Hello all, our project is on symbolic execution of angr. First off, let's try to understand why this problem is important. Software contains bugs and manually exploring large code bases is ineffective. To facilitate automated study of software, several program analysis techniques have evolved that allow study of software properties such as, does this code base dereference a null pointer, or does it contain a backdoor that bypasses authentication? The two of the most common techniques are static and dynamic analysis. Static analysis studies a program without executing it, while dynamic analysis does the same by executing it. While there are a lot of commercial and open source tools that support this, their adoption is limited due to scalability concerns and their ability to achieve good coverage. Symbolic execution hits a middle ground and generalizes software testing. In symbolic execution, a program is executed on symbolic inputs. Path constraints are generated for each control flow path of the program, which is then supplied as input to a solver. Solver returns a set of values that will satisfy the path constraint.
Now that we know what symbolic execution is and why we care about it, let's take a look at an example of how it works. So let's say we want to symbolically execute this function on the left, get sign. We're going to pass it a symbolic argument of x. And so what our symbolic execution engine is going to do is as it goes along and executes a program, it's going to generate these path constraints every time we hit a branch statement. And so once we end up hitting a return statement or an assert statement, then the engine is going to generate a test case that satisfies those path constraints. And so as we can see here, we'll end up with 3 possible tests based on 3 possible paths of execution. So that was a simple example of symbolic execution where we don't access memory, but since most of our programs do access memory, it's important that we are able to handle that in our symbolic execution engines. So in this example, we have a memory object A being accessed by symbolic indices I and J. And so since these symbolic indices could really point anywhere in A, it turns out it's kind of hard to determine whether or not the bomb is going to explode in this example. And so it's important our symbolic execution engines are able to explore interesting paths of our programs, even if they access memory symbolically. So yeah, this is a motivating example for why we need efficient, fully symbolic memory. So these are a couple of popular symbolic execution frameworks. The one we're focusing on in our project is called angr, and it's very convenient because you can perform analysis on arbitrary binaries without requiring a source code of an application, whereas cleave requires source code because it's built on top of the LLVM compiler and operates on LLVM bytecode. And angr is also useful because you get a nice convenient Python REPL to interact with.
I'll now formally introduce the problem statement. The problem is that angr's support for symbolic memory is inefficient and unscalable. This leads to aggressive concretization when handling symbolic reads and symbolic writes for complex programs. Concretization is bad because concretization leads to missing paths and thus missing bugs. So our goal is to enhance angr's memory model to be able to support efficient symbolic reads and efficient symbolic writes. Our solution to the problem is memsite. Memsite is an algorithm for efficiently handling symbolic memory without having to resort to any concretization that was developed by researchers in Rome. There currently exist two implementations, one based on cleave and one based on a really old version of angr. The angr version of memsite has been shown to be able to perform a much more precise analysis for complex programs than plain angr can. And our efforts are primarily focused around porting memsite to the latest version of angr. Several types of memory models have been proposed in the literature. These primarily differ in how they handle the multiple resolution case. The memsite algorithm is the closest to the merging model on this list, which is more scalable than the forking model, but less so than the segmented model. The forking model is implemented by cleave, and the segmented model has been explored in the fork of cleave and shown to be the most scalable of all the ones out there.
So let's take a look at the key limitations of the angr codebase. So angr does support fully symbolic reads and partially symbolic writes, but their approach to this process is not all that efficient. And so by default, if a read has a possible range of more than 1 kilobytes worth of values, then it will end up concretizing that read to just one of the addresses in the range that was specified. And the same holds true for writes, but with a range of only 128 values, which is fairly limiting in terms of exploring all of a program's possible paths and behavior. And so here we see those ranges imposed again in another portion of the code base.
The approach we have taken for this project is to leverage upon MemSite's work that has augmented angr to support fully symbolic writes. They have a wrapper around angr for the same. The downside is that they use a version of angr that is 10 releases old and requires Python 2, whereas the latest angr requires Python 3. Currently, we have ported the MemSite installer for latest angr version and Python 3 and also converted the code base to support Python 3. Based on angr's changelog, we are trying to port angr to an intermediate release that has significant update to core objects. However, there are a few challenges we have encountered. A diff of the code base of the two angr versions reveal major code changes and refactoring, including changes to angr's core objects. While we succeeded in installing the intermediate version of angr, all the memory tests have failed. We have also observed patches that break the code. We are currently in the process of debugging it. Finally, we would like to thank Guffey for his guidance and constant support. Thank you for watching our presentation.